Today we are going to discuss electric field. What is a field? Field is a concept introduced in order to explain non-contact forces. There are different types of non-contact forces. For example, force between two bodies, gravitational force between two magnets, magnetic force, and force between two charges, electrostatic force. In order to explain force between two bodies, we introduced gravitational field that we already studied last year. In order to explain force between two magnets, we can introduce a magnetic field, as well as in order to explain force between two charges, we introduce electric field. The concept of electric field can be explained using this particular diagram or this particular representation. There are two charges. This is the first charge and this is the second charge. There's an interaction between these two charges, and that interaction may be either attractive in nature as well as repulsive in nature. If the charges are like, repulsive force comes into play, or if the charges are unlike, attractive force comes into play. Actually, what is happening, the first charge sets up a field, and the second charge, if it is comes inside the field of first charge, there will be interaction. So actually, charge-charge interaction takes place with the help of an intermediate called field. If it is the reverse also possible, second charge sets its own field. If the first charge comes inside the field of second, there will be interaction. If the first charge is not inside the field of second, there will not be interaction. So in order to explain charge-charge interaction, we use an intermediate concept, and that intermediate concept is called a field. In simple language, electric field can be defined as space around a charge or a charge distribution where its effect can be felt. Once again, the space around a charge or a charge distribution where its effect can be felt, that is what electric field. And what is the effect of a charge? Effect of a charge is attraction or repulsion on another charge. So electric field can also be defined as space around a charge or a charge distribution where another charge experiences an electrostatic force. Once again, electric field is defined as a space around a charge or a charge distribution where another charge would experiences an electrostatic force. So the definition of electric field goes like that. Okay. Now we are going to represent mathematically the electric field. Mathematically, the electric field is defined as the force experienced per unit charge. So if there is an electric field, I am going to place a charge, a positive charge over there, then the force per charge is the electric field at that point. So it is defined like this: electric field at any point R is equal to electrostatic force per unit charge. So the charge we are using is the name given for this particular charge is test charge. So usually it is denoted by Q0. Test charge is nothing but a small positive charge. So electric field at any point is the electrostatic force per unit charge at that point. Since it is force per unit charge, its unit will be Newton per Coulomb, because force is measured in Newton, charge is measured in Coulomb, and it is also measured by volt per meter, that we can study later. Now, the test charge should be very small. Why the test charge should be very small, I can explain using this particular figure. So actually, I have a charge distribution. Maybe a conductor which is charged by positive charges like that. So this charge distribution create an electric field around it. So at this particular point, at a distance r from the center, I have to find out electric field. According to this definition, the electric field is the force per unit charge. So in order to find out the force, I am going to place a charge Q0 over there. But this charge Q0 is of a big magnitude. Here is the electrostatic induction. Due to electrostatic induction, free electrons shift closer to this test charge, and positive charge shift away from the test charge. The nearer end of the conductor acquire more free electron and the farther end of the conductor acquire positive charge. Therefore, what happens, what is the net effect? The positive charge on the surface of the conductor nearer to the test charge decreases and positive charge on the surface of the conductor away from the test charge increases. So actually there is a shift in the center of charge from the center of the sphere to slightly away. R, the effective distance between this test charge and this charge distribution increases. When R increases, electrostatic force decreases. So the force which we measure here is not actual force, it is measured force that is lesser than actual force. The intensity of the electric field is force per test charge or unit positive charge. That means since the force measured is lesser, the electric field measured is also lesser. So even though the electric field E is here, we will never measure electric field E if this charge is of fair amount of magnitude. So this problem can be avoided by using a very small positive charge as the test charge. If I am using a very small positive charge as the test charge, that will not create that much electrostatic effect on this charge distribution, and the force measured will be actual and electric field measured also will be actual. So that is why intensity of the electric field can be written like this: ER is equal to limit Q0 tend to 0 FR divided by Q0. Q0 tend to 0. What's the meaning of that? The test charge taken should be very small. It is not equal to 0, but it is tending to 0. Means it should be very small. It will not create any electrostatic effect on another charge distribution. So this can be considered as the general equation for electric field at any point. Now we are going to study what is the electric field due to a point charge. Let us take a point charge Q. This point charge creates a space around it where its effect can be felt, and that space is called electric field. Now I want to measure intensity of electric field at this point P at a distance R from this source charge. So in order to find intensity of electric field, I have to place a test charge Q0 over there, a very small positive charge. So then there will be an electrostatic force F is equal to 1 by 4 pi epsilon 0 Q0 by R square. Now the intensity of electric field E is equal to F by Q0 1 by 4 pi epsilon 0 Q0 by R square into Q0. So Q0 cancel. What remains is electric field intensity E is equal to 1 by 4 pi epsilon 0 Q by R square into unit vector R. Unit vector R indicate the direction of electric field. If it is a positive charge, electric force will be outwards and electric field also will be outwards. On the other hand, if the source charge is a negative charge, the force on a test charge will be inwards towards the negative charge, the electric field also towards the negative charge. Now this equation is applicable only if the charge is placed in air or free space. If the source charge is placed in any other medium, the equation for electric field intensity E is equal to 1 by 4 pi epsilon Q by R square into R, where epsilon is the absolute permittivity of that medium. Now we already studied that epsilon is equal to epsilon 0 epsilon R. Substituting here, we will be getting E is equal to 1 by 4 pi epsilon 0 epsilon R Q by R square into R. And that equation can be considered as a general equation for electric field intensity at any point irrespective of the medium. It is applicable for all mediums. Now look at what are the factors affecting electric field. The first one is electric field is proportional to source charge. If intensity of the source charge increases, electric field also increases. The second one is electric field is inversely proportional to distance square. as the distance from the charge increases, electric field decreases. The graph between electric field and distance is like that. Third one is electric field is inversely proportional to absolute permittivity or relative dielectric constant. As the dielectric constant of the medium increases, the electric field decreases. Now we have to study the superposition principle. Superposition principle says that total electric field at any point due to a system of charges is the vector sum of the electric field due to individuals. So this is the point P surrounded by a system of charges Q1, Q2, Q3 at distances R1, R2, R3. Each charge creates an electric field over here, and the net electric field is the vector sum of the electric field due to individuals. So I can write E1 as 1 by 4 pi epsilon 0 Q1 by R1 square into R1 unit vector plus 1 by 4 pi epsilon 0 Q2 by R2 square into R2 unit vector, etc. Using summation notation, I can represent E is equal to 1 by 4 pi epsilon 0 summation I is equal to 1 to n Qi by Ri square into Ri. This particular equation gives the net electric field or total electric field at any point due to a system of charges. Now, one more thing I want to discuss in this particular section. Consider a positive charge placed inside an electric field. This is a positive charge placed inside an electric field E. Then there exists a force F is equal to QE. And what's the direction of electric field? Direction of electric field is in the direction of force is in the direction of electric field. And this equation comes from this equation itself. We know that E is equal to F by Q, therefore F is equal to E into Q. Therefore, the force experienced by a positive charge inside an electric field is equal to Q into E. The direction will be in the direction of electric field. On other hand, if it is a negative charge, the magnitude of the force remains same, but look at the direction of electric field and direction of force. The electric field is in this direction, but negative charge experiences a force opposite to the direction of electric field.